right, before we start our problem solving session, which I'll probably also put on another video because I like to keep the mechanisms very separate, but the converting an alcohol into a tosylate group. Now, this is what we call p-tosyl-chloride. It also stands for, because you see how this group is, let's start numbering some things. 1, 2, 3, 4. Whenever we have two groups connected to a benzene and it's a distance of 4 apart, we call it para for P. Then we have this picture, which we'll learn how to name benzenes later, which is called toluene. Then sulfonyl chloride. So that's where we get the p-tosyl chloride. Understanding how it looks may make a difference to you for future reference, but the same idea. You have an alcohol and you have to go through and now start the mechanism for it. Now, how do we do that? Well, the alcohol, again, is the bad leaving group, and it has lone pairs that we're going to attack the sulfur with and kick out the Br. So now when we do this, we have to understand the next portion. Does anything change yet with the stereochemistry of my alcohol? The answer is no. So what we're doing is just attaching the group, and you'll see sometimes I'll put a circle in the middle. That still just means the double bonds, but they're consistently moving, which is fine. So that's the first step of the mechanism of the alcohol attacking the sulfur group. Then you get your unstable molecule. You will take the pyridine and use its lone pairs to stabilize the oxygen. So you're grabbing the hydrogen and causing the oxygen to stabilize, giving you this picture. Now, as you can see, the stereochemistry of the structure stayed the exact same. This is all the mechanism requires. So it's showing you that when you have a tosylate group, when you go to try to create or make this alcohol a good leaving group, it's a better leaving group because of the size. The bigger something is, the quicker it leaves. Now, I'll actually continue and put the problem solving one on this video so you don't have as many videos to go through. So tosylates keep the stereochemistry of the original alcohol the same. When using the SOCL2, so it's little things. When we use the p-tosyl chloride, the alcohol, once we do the leaving group and add that on there, the stereochemistry doesn't change. So no change in stereochem. But the second we use the SOCL2 or the PBR3, both of these will go through an SN2 mechanism on both sides, which will cause whatever you started your structure with. So if you started with R, it would end as an S. If it started with an S, it would end as an R. So these will always cause inversion of stereochemistry. So now when we do the problem, hopefully breaking it down into this chart also helps. So let's go over this. So how do we know what to use when they give us a problem? So here I see my starting structure, which again, you can go through and designate the R and S notation for good practice. This is an R notation. And over here, this is an S notation. Now, I see a complete inversion happen, but this is not a Cl. It's not a Br, it's something completely different that they added into the picture. So they want to know, how did I start from this conversion and land here? So how do we know how the two different groups act on an alcohol? Well, since we said this one's SN2, we immediately should see a Br or a Cl written like this in order to accompany the SN2 reaction. Now we see that they added an OCH3. Again, sometimes people are like, where did that come from? The instructor should have provided it, in all honesty. So in this case, Na is an ion, so just like Li in potassium K, they will always have a positive charge and never add into the picture. So we're really looking at this OCH3. Understanding, if I start off SN2, I'm going to continue using SN2 all the way, which would give me now this picture of an OCH3. Well, we have a problem. I had inversion in between, but at the end of the day, it pretty much retained the same stereochemistry. Now, compared to the p-tosyl chloride, you're going to see me abbreviate it here, because that p-tosyl chloride, to write that out, ain't no joke. So when this gets added, this is automatically going to retain. So there's another shorthand way you could put this. You could just put O, tos, like tosyl TS, to make life easy. Then it retained the stereochemistry. So right here, we had retention of stereochemistry. But as soon as we bring in a base, I'm able to go back and complete SN2, which would allow my picture to look like the original one I needed. So in summary, to say this, if we are given an alcohol that has stereochemistry and we notice that we have an inversion at the end, I had to retain it, then invert it to get this answer. It's the only way, which lets me know I had to use route number 2 and not route number 1. If I had seen that this picture looked the exact same in my product, but with a different group attached, anything that starts one way and ends in almost the same look, that is going to be required for you to use route 1, which is the PBR3 or the SOCL2. Really study this problem. I have a hint that it may be on your exam.